Okay, let's talk a little bit about the types of routing protocols. Routing protocols can be classified into different groups according to their characteristics. Specifically, if the routing protocols can be classified by either their purpose, their operation, or their behavior. The purpose is interior gateway protocols or exterior gateway protocols. And if you'll notice here on the right, here we have the interior gateway protocols or the exterior. We're going to look at their operation. Are they distance vector, link state, or path vector? So here we have distance vector protocols, link state protocols, and path vector routing protocols. And then their behavior. Are they classful, which means that they're legacy? That's our RIP v1 in IGRP. Or are they classless? RIP v2, EIGRP, OSPF, ISIS, or BGP. RIP v1 is legacy, IGRP is legacy, RIP v2 is IGP, it's distance vector, and it's classless protocol. You'll need to make sure that you can pick out which one of the protocols fits either in the distance vector routing protocol or link state, if they're interior gateway or exterior gateway, and you know that these are all dynamic routing protocols. Now we have what's called an autonomous system. And an autonomous system is a collection of routers under a common administration, such as a company or an organization. And the autonomous system is also known as the routing domain. Typical examples of an autonomous system are a company's internal network and an ISP's network. The internet is based on the autonomous concept. So you have two types of routing protocols there. We have your interior gateway protocols, the IGP. And again, remember that our interior gateway protocols are RIP, EIGRP, OSPF, and ISIS. Exterior gateway protocols are EGP, and they're used for routing between your autonomous systems. It's also referred to as inter-AS routing. Service providers and large companies may interconnect using EGP, and the border gateway protocol BGP. And it is the only currently viable EGP protocol, and it's the official routing protocol used by the internet. Now, distance vector. We're going to talk a little bit about it first. Distance vector means that routes are advertised by providing two characteristics, distance and vector. The distance identifies how far it is to the destination network and is based on a metric such as a hop count, cost, bandwidth, delay, and other things. Your vector specifies the direction of the next hop router or exit interface to reach that destination. An example here is with this figure to the right. Router 1 knows that the distance to reach network 172.16.30 is 1 hop and that the direction is out the serial interface 000 towards router 2. A router using a distance vector routing protocol does not have the knowledge of the entire path to the destination router. It knows its next hop. Or its next location. The distance vector protocol uses routers as signposts along the path to the final destination. The only information a router knows about a remote network is the distance or the metric to that network. And the distance vector routing protocols do not have an actual map of the network topology. There's 4 distance vector IPv4 IGPs. You have RIP v1, RIP v2, IGRP, and EIGRP. So the 2 different versions of RIP and the 2 different versions of IGRP. The RIP v1, IGRP are legacy or first generation, and then the RIP v2 and EIGRP are the more current of the 2. In contrast to your distance vector, you have link state protocol. And routers configured with linked state can create a complete view of the topology of your network by gathering information from all the other routers. So instead of just knowing its next hop, it's going to learn about your entire network. To continue the analogy they were using on Signpost, using a linked state routing protocol is like having a complete map of your network topology. So with distance vector, we're going to the next signpost, and from there we'll go to the next signpost. In linked state, you have the whole map in front of you, and you can map out your routes from there. RIP-enabled routers send periodic updates of their routing information to their neighbors. Linked state routing protocols do not use periodic updates, and after the network has converged, a linked state update is only sent when there's a change in the topology. So there's not as much activity going on with the routers as a part of its administration of your routing table. The only time the linked state is going to send something else out is if a router is added to your network, or if a interface goes down and it's having to reroute the traffic. Your linked state protocols work best when the network design is hierarchical, usually occurring in your large networks, when fast convergence of the network is crucial, and the administrators have a good knowledge of the implementation of linked state routing protocol. And these are OSPF and ISIS. Next, one of the biggest distinctions between classful and classless routing protocols is that classful routing protocols do not send your subnet. Okay, remember, with classless, it's when we're breaking things down, we're able to subnet our IP addresses, we're able to break down our networks, and we have a subnet mask. So with a classful, we do not include the subnet mask. With classless, we do. With that said, our classless routing protocols support the VLSM in the CIDR. IPv6 routing protocols are considered classless because we don't have the subnet mask with them. The distinction whether a routing protocol is classful or classless typically only applies to our IPv4 routing protocols. All of the IPv6 routing protocols are considered classless because they include the prefix length with the IPv6 address. Now let's compare our routing protocols. We can compare them by looking at speed of convergence, their scalability, classful or classless, their resource usage, and the implementation and maintenance. So with speed of convergence, you're looking at how quickly the routers and the network topology share routing information. How quickly do they converge? Scalability defines how large a network can become. That's important if you expect your company to grow. If you expect it to stay small, then you'll go with a small protocol. If you expect your business to grow, you want something that is very scalable. Classful or classless means, are you going to use the subnet mask? How are you going to do that? Resource usage includes the requirements of a routing protocol, such as the RAM. How much RAM is it going to use? How much CPU does it use? The link bandwidth utilization. Higher resources requirements usually means that it's going to make your system slow down to a bit. And then implementation and maintenance. How much knowledge do you need to know in order to implement these protocols? The chart here to your right is a good one for you to commit to memory, or at least have readily accessible to you as we go through this. There are cases when a routing protocol learns of more than one route to the same destination. This example here, PC1 can send information to PC2, but you'll see there's several different ways he can get there. To select the best path, your routing protocol must be able to evaluate and differentiate between these paths. So it's got to look at several different things. A metric is a measurable value that's assigned by the routing protocol to different routes based on the usefulness of that route. The routing metrics are used to determine the overall cost of a path from the source to the destination, and routing protocols determine this, or the best path, based on the route with the lowest cost. So how quickly can it get there? Different routing protocols use different metrics, and the metric used by one routing protocol is not comparable to a metric that's used by a different routing protocol. They don't always come up with them the same way. The animation, if you take the time to watch it, shows the difference between RIP and OSPF. You'll notice that these three connections, one is a 56 kilobyte connection, the other two are T1 lines. So RIP is going to look at it one way, and OSPF will look at it a different way. So let's watch this. So the RIP goes out, it shows the route directly from router 1 to router 2. However, OSPF went what you would think by observation and looking at it would be a longer route. But the OSPF sees that the bandwidth that it's using, or the metric to go across the two T1 lines, was quicker than going across that 56K line.